Chapter 4 begins on page 26, and it's a picture of a man, and it's blue. So let's read the caption on the page 27. It says, Basic Chemistry. I tell my students to try to know molecules so well that when they have some question involving molecules, they can ask themselves, what would I do if I were that molecule? Down at the bottom, we can see that the father of modern chemistry is Antoine Laurent de Lavoisier in his laboratory. I don't pronounce French names very well. Turn the page to 28, please, and we always start by looking at our chapter and looking at the major headings. At the top of chapter 28, oh my goodness, in the top of page 28 in black letters it says Basic Chemistry. Then in the middle of page 28 in blue it says Atoms. Turn to page 31 and in blue letters up at the top it says Molecules. Turn to page 32. At the top it says Mixtures. In the middle of page 32 it says Are we afraid of chemicals? In blue. Then at the bottom of page 33 it says Periodic Table of Elements. And turn to page 34 and 35, and on page 35 you can see the periodic table of elements. And that's it for the whole chapter, so let's go back and start reading at the top of page 28, Basic Chemistry. Before beginning to study the smallest living creatures, we must first study atoms and molecules, the tiny building blocks of matter which make up all creatures. Chemistry is the study of how atoms and molecules interact with each other. Living things are powered by interactions between atoms and molecules, so it is important to understand the basics of chemistry before studying life science. Atoms on page 28. An element is a simple substance that cannot be broken down by ordinary chemical means. For example, carbon, oxygen, and sodium, those are all elements. An atom is the smallest part of an element that still has all of the properties of the element. Atoms are extremely tiny, so we always have many of them, even in a small piece of material. An element is made up of many atoms of the same kind. An atom is so tiny that even using the best compound microscope on Earth, you can't come close to seeing one. With a special electron microscope, which uses a beam of electrons instead of light rays to look at things, you can actually magnify objects 10 million times. At that power, atoms can be seen, but they appear to be indistinct, hazy dots. Top of page 29, please. How big, or shall we say, how small are atoms? According to chemists, there are approximately 1.5 times 10 to the 22nd atoms in one drop of water. That's 15 billion trillion. That is 15, 000, 000, 000, 000, 000, 000, 000, atoms in one drop of water. A medium-sized atom is about 10 to the negative 10th power of meters. That is 0.0000000000001 meters in diameter. For comparison, you are about 1.5 meters tall, which is 10 billion times larger than an atom. As tiny as an atom is, it is made of 3 main pieces, even smaller yet. In the dense center region of an atom is the nucleus. In the nucleus there are protons with a positive electric charge, and neutrons, which are neutral. That means no electric charge. Spinning crazily around the nucleus in energy shells are tiny particles called electrons, which have a negative electric charge and are much smaller than protons or neutrons. You should be familiar with electrons because they are electricity. These three pieces take up very little room, and most of the atom is empty space. Scientists often use Bohr models, such as the ones below, to draw the parts of an atom. It is important to realize that Bohr models are not drawn to scale. The electrons in an atom are actually much, much smaller than the nucleus and are much farther away. So look at the figure on the bottom of page 29. There's a carbon atom and a sodium atom. And notice the energy shells, those are the rings around there. And you can see that the electrons have an E with a negative sign. Those have a negative charge. In the center of the blue nucleus, there's a neutron with an N and a zero after it. That means there's no charge. And a P, which is protons, which have a positive sign because there's a positive charge. Turn your book to page 30, please. So there on 30, you have a bunch of elements up at the top. So up at the top, you can look at the symbol. So let's just do the top one. The symbol is H. The name is hydrogen. There are one proton, one neutron, and one electron, and then each element has some notes. So the note for hydrogen says it exists as H2, an explosive gas, one of two elements in water, needed for protoplasm. About 9.5% of you is hydrogen. So down below, let's just kind of go down the chart on page 30. H is for hydrogen. Drop down. C is for carbon. Drop down again. N is for nitrogen. Drop down. O is for oxygen. And then let's read the words in the white space. It says, the four elements above make up almost all of the bodies of microbes, people, and the gigantic blue whale. The elements listed below are necessary in very tiny amounts. So below that we have Na, which is sodium. It's pronounced natrium in Latin, and that's why it's Na. Mg is magnesium. P is phosphorus. S is sulfur. Cl is chlorine. K is potassium, and it's symboled with a K because in Latin it's kalium. Ca for calcium. Fe for iron, and in Latin it's ferrum, that's why it's Fe. Copper is Cu, but in Latin copper is cuprum, so it's Cu. Zn is zinc, and I is iodine. So I want you maybe pause this right now and look at all of the information about the protons, neutrons, electrons, and the notes about each of these, and then let's read at the top of page 31. Top of page 31. Atoms with the same number of protons in their nuclei are the same kind of atom. If two atoms with different numbers of neutrons and electrons have the same number of protons, they are still the same kind of atom. One of more than 100 kinds of atom, 92 may be found in nature. For life science, the 15 kinds of atoms shown in figure 4.4, which is page 30, are the most important. Memorize the name and the symbol for each of them. Let's read on page 31 in blue, molecules. Just as an individual atom is a single piece of an element, a molecule is one individual piece of a compound. A compound is a pure substance made of two or more elements. The different elements in a compound must be chemically joined in a definite ratio. For example, when atoms of hydrogen and oxygen combine in a 2-to-1 ratio, they form water, which is H2O molecules. This happens in a chemical reaction, which can occur quietly in your cells or very loudly when hydrogen gas explodes. We can write the equation for the chemical reaction like this. 2H2 plus 1O2 makes 2H2O plus energy. This chemical equation describes a chemical reaction that starts with two molecules of hydrogen gas, which is H2, and one molecule of oxygen gas, which is O2. First, the atoms of hydrogen in the molecules of H2 gas separate, and the atoms of oxygen in the molecules of O2 gas do the same. When two atoms of hydrogen join one atom of oxygen to make water, H2O, gone are the explosive hydrogen gas and oxygen gas that was needed for burning. In their place is the compound water, which, when cooled, is a liquid. Cooled below 0 degrees Celsius, water becomes a solid. Remember, atoms are pieces of elements, and molecules are pieces of compounds. There are only 92 natural elements, but there are millions of compounds because the elements can combine in thousands of different ways. In life science, we will concentrate only on just a few of the millions of compounds. About 60% of the human body is water. If you weigh 100 pounds, almost 60 of those pounds is water. You might think, I'm all wet. You'd be 60% correct. Most of the rest of your physical body is made of compounds with carbon in them, called organic compounds. A future chapter on nutrition will discuss the very large molecules in 3 groups of compounds: carbohydrates, such as sugars and starches, lipids, such as fats and oils, and proteins, like hair, muscles, and enzymes. There are several small inorganic compounds that are also important for life science. NaCl is table salt, HCl is hydrochloric acid, and CO2 is carbon dioxide. Turn your book to page 32, please. Mixtures at the top of the page. A mixture can be formed when different kinds of compounds or elements are together but still keep their own properties. The liquid part of your cells, which is called protoplasm, is a mixture of water and many other compounds. The liquid part of your blood, which is called plasma, is also a mixture. If you had to pick just one thing on Earth most like your body's liquids, what would it be? Remember, you are mostly water. 60% of you, that is water, is not pure water though. In the water of your body are dissolved salts, oxygen, and carbon dioxide gases and organic compounds. The one thing on Earth the most like your body's liquids is seawater. The oceans are mostly water, but they contain dissolved oxygen and carbon dioxide as well as organic compounds. As a matter of fact, when your life began inside of your mother, you were surrounded by a little ocean all your own, the amniotic sac. It is because of these similarities that some people think that all living things must have come way back in time from something in the oceans. But life is much more than just seawater. Organisms, even the most simple, are very neatly organized and well planned. Middle of page 32, are we afraid of chemicals? Compounds which scientists use in chemical processes are often called chemicals. Chemical has become quite a negative word to many people, perhaps because of chemical spills, chemical warfare, and chemical dependency. One reason that it can be hard to think positively about chemicals is because many people are unfamiliar with chemicals, or at least with their names. For example, do you have tetrahydrozoline hydrochloride in your home? You may recognize this chemical if I tell you that it is one brand of non-prescription eye drops. Some chemicals are familiar, such as aspirin, rayon, gold, oxygen, and caffeine. It is when we hear a name like hydrogenated glucose syrup that many of us become uneasy, only to find out that this chemical is an ingredient in many sugarless gums. Some people try to label chemicals as good or bad. They believe that bad chemicals cause tragedies. However, no chemical is good or bad. How they are used determines whether or not chemicals will be beneficial or harmful. Many chemicals made by man are natural also. Hydrochloric acid is used in many industrial applications, but it is also produced in your stomach naturally. Do not fear chemicals. Learn about and understand them. Turn to page 33, please. Let's read up at the top about Antoine Laurent de Lavoisier. Let's hope I pronounced that correctly. All right, Antoine, we're just going to call him that, was a modern, Antoine, 1743 to 1794, was a Catholic scientist who is also known as the father of modern chemistry. His greatest contribution to chemistry was his insistence that science must be based on a strict observation of the facts. For instance, in Lavoisier's day, scientists believed that a substance called phlogiston was given off when materials were burned. The theory of phlogiston was a good hypothesis, but unfortunately scientists accepted it before it was proven by rigorous experiments. Unlike many other chemists, Lavoisier did not think that the theory of phlogiston had been proved sufficiently, and he was right. After experimenting for a long time, Lavoisier showed that when materials are burned, they take a certain gas out of the air, instead of putting phlogiston into the air. Lavoisier called this gas oxygen, the name that we still use today. Lavoisier's careful experiments transformed chemistry into an exact science based on definite rules. He also classified everything that was known about chemistry at that time, and that giving elements the names that they are still used today. His list of elements forms the basis for the modern periodic table of elements. Unfortunately, Lavoisier's scientific career was interrupted by the French Revolution, which had condemned him to the guillotine because he had held a government position in the old French monarchy. Lavoisier's biography writes, "Raised in a pious family, which had given many priests to the church, Lavoisier held to his beliefs." So the guillotine is the machine that they go into to get their head chopped off. So poor Lavoisier. We'll keep him in our prayers, right? Okay, bottom of page 33, let's read the periodic table of elements. The periodic table of elements shows the symbols for all of the known elements. The elements in the periodic table are arranged in order of increasing atomic number. An element's atomic number is the number of protons which it has in its nucleus. For instance, the atomic number of carbon is 6, which means that it has 6 protons in its nucleus. The small numbers in the top right corner of each element represent the number of electrons in each energy shell. You can see from figure 4.8 on the right side that carbon has 2 electrons in its first energy shell and 4 electrons in its second energy shell. Turn to page 34, please. The 18 vertical columns in the periodic table are called groups. Elements within a group have similar properties and contain the same number of electrons in their outermost energy shell. A horizontal sequence of elements is called a period. In a given period, the properties of the elements gradually pass from a strong metallic to a strong non-metallic nature, with the last number of a period being a noble gas. Metals have only 1 or 2 electrons in their outer energy shells, which they can easily lose to bond with other elements. This makes elements very reactive, so they cannot readily be found in a pure state. All metals are good conductors of electricity and heat and can easily be stretched and shaped. The transition metals are less reactive than the metals in group 1 and 2, and many can be found naturally in a pure state. Nonmetals are poor conductors of heat and electricity. They are brittle when in a solid form and cannot easily be stretched or shaped. The noble gases are very stable because they have the maximum number of electrons in their outer energy shell and hardly ever form compounds with the other elements. The inner transition elements include many synthetic and radioactive elements. Synthetic elements are those which do not occur in nature, but have been created by scientists in laboratories. Hydrogen is a unique element and shares properties of metals and nonmetals. I'm going to let you look at the periodic table of contents, the periodic table of elements on page 35 and figure that whole thing out. See you next time. Bye-bye.